The Grand Experiment, A Narrative History of Science and Discovery. Chapter 1. The Dawn of Curiosity. Prehistoric Observations and the Seeds of Wonder. Before humans had words to describe the warmth of the sun or the sparkle of the stars, they had eyes to see, ears to hear, and minds that wondered. The earliest glimmers of scientific thinking likely emerged around campfires beneath starry skies, where prehistoric humans, without the luxury of writing, observed the rhythms of day and night, the turning of seasons, and the quiet interplay of life and death. These first inklings of curiosity, though unrecorded, paved the way for the massive edifice of knowledge we would someday call science. In those distant epochs, survival demanded careful observation of nature. Hunter-gatherers needed to distinguish between edible and poisonous plants, track migrations of game animals, and predict the changing weather. While these behaviors were grounded in immediate necessity, they were also the seeds of something new, the systematic investigation of the environment. Artifacts like carved bones or tally sticks from the Paleolithic period may have served as rudimentary counting tools. What might look to us like mere scratches could have been early calendars or attempts to record the moon's phases. Across the globe, as human populations expanded, settled, and eventually created societies, they carried with them cumulative knowledge. Though pre-literate, these communities had developed ways to pass on lore, through oral tradition, myths, and rituals. The night sky, studded with constellations, was a shared canvas for storytelling. Over millennia, these shared observations of the heavens would help people navigate land and sea, shape agricultural calendars, and eventually give birth to astronomy. It's thrilling to imagine a Paleolithic father teaching his son which stars to follow when traveling by night, or a group of elders ceremonially relaying the significance of certain plants for healing. Such moments, though we can only guess at them, were the building blocks of everything that science would eventually become. Through repeated trial and error, people discovered consistent outcomes. Boiling water killed unseen threats, rotating crops improved harvests, and a certain arc of the sun foretold a new planting season. One of the earliest sciences that prehistoric peoples practiced was practical medicine. From pre-literate times, we find evidence of rudimentary surgical procedures, such as trepanation, drilling a hole in the skull. Though the logic behind it may have been shrouded in superstition, the fact that it happened points to an experimental approach. Some condition was believed to be alleviated by removing a piece of skull. Whether for spiritual reasons or crude medical necessity, it involved early hypotheses about the link between body and health. In this way, the scientific impulse, observation, hypothesizing, testing, was already being exercised long before the formal structures of the scientific method existed. The daily quest for food, shelter, and community forced early humans to develop an intuitive approach to problem solving. When a technique seemed to work, it was repeated and shared. When it failed, it was modified or discarded. Thus, in fits and starts, the seeds of inquiry were quietly planted. On every inhabited continent, Neolithic communities built structures that may have doubled as astronomical observatories or communal gathering places. The ring of standing stones at Stonehenge in England and the arrangement of giant megaliths at Nabta Playa in Africa are just two examples. These constructions show an emerging sophistication. People aligned stones or markers to the solstices or to certain stellar risings. In these archaic monuments, we see the earliest footprints of observational astronomy, linking cosmic events to earthly needs, such as predicting harvest or religious celebrations. Nevertheless, this was all still pre-scientific in a strict sense. Mythology often interwove with observation. A constellation might be revered as a god's chariot, portending good or ill fortune. A solar eclipse might be attributed to a mythical beast devouring the sun. Yet such explanations did not preclude meticulous record-keeping or consistent application of knowledge. Indeed, the mixture of myth and observation was typical in pre-literate societies, serving as a kind of proto-science that laid the groundwork for the more systematic inquiries to come. Today, as we sift through archaeological evidence, from cave paintings to megalithic sites, we catch fleeting glimpses of a time when the line between practical knowledge and magical thinking was blurred. Yet even in that blur, we see the basic impulses that would eventually culminate in the scientific method: observe, question, test, and infer. Though it would take millennia for these impulses to bloom into formal theories and experiments, the spark was already lit in the curious minds of our ancestors. Thus the story of science begins in shadows and flickering firelight, with hands that reached out to touch the unknown and minds that dared to ask, why? From these humble beginnings, the stage was set for the great civilizations of the ancient world, who would further shape and codify our species' quest to understand nature's secrets. Chapter 2: The First Civilizations. Babylonians, Egyptians, and the architecture of early knowledge. As humans congregated in river valleys, from Mesopotamia to the Nile, knowledge began to accumulate in more organized forms. Around 4000–3000 BCE, in the Fertile Crescent between the Tigris and Euphrates, the Sumerians cultivated fields, built city-states, and invented cuneiform writing. Meanwhile, along the Nile, Egyptian culture flourished, giving rise to monumental architecture and sophisticated mathematics. These first civilizations, each in their own way, expanded the horizons of scientific observation. One of the hallmark achievements of ancient Mesopotamia was the development of written language. Cuneiform wasn't just for recording taxes or royal decrees. It also provided the means to document astronomical observations, medical diagnoses, and mathematical rules. Babylonians created detailed star charts, noticing that certain celestial bodies wandered against the backdrop of fixed constellations. These wandering objects, what we now recognize as planets, became the focus of intense study. Babylonian astronomers could predict lunar eclipses and chart planetary positions with impressive precision, despite lacking telescopes. Egypt, too, made staggering advances. The construction of pyramids required extensive planning, geometry, and surveying techniques. Egyptians figured out ways to measure time through sundials and water clocks, dividing the day into hours. Their mathematical papyri reveal operations that approximate pi and solve practical problems related to building projects. Perhaps even more critical was the Egyptian approach to medicine. Preserved papyri like the Edwin Smith Papyrus and the Ebers Papyrus outline treatments for wounds, references to anatomy, and even descriptions of surgical procedures. Though wrapped in religious or magical contexts, these texts also reflect an empirical tradition, where cause and effect, at least in a rudimentary sense, were observed and recorded. The religious and social structures of these civilizations were deeply entwined with their proto-scientific investigations. In Mesopotamia, astrology was inseparable from astronomy. Priests studied the heavens to interpret omens, believing celestial events mirrored the affairs of gods and kings. In Egypt, pharaohs were seen as divine or semi-divine, so the construction of monumental buildings had religious significance as well as demonstrating engineering prowess. While we might think of these pursuits as magical, they still required systematic observation and problem-solving, key components of scientific inquiry. Babylonian mathematics introduced place-value systems and paved the way for algebraic thinking. Although their base 60 sexagesimal system might seem arcane to modern eyes, we still use elements of it today: 60 minutes in an hour, 360 degrees in a circle. These are echoes of Babylonian achievements. They kept extensive tables of multiplication and reciprocals, demonstrating an early form of computational science. Egyptian engineers had to calculate the slope and alignment of pyramids and temples. They used primitive but effective tools like the level and the plumb line to ensure correct angles. The legendary Imhotep, architect, physician, and later deified as a god of medicine, symbolizes the fusion of religious authority and technical skill in ancient Egyptian culture. The stories about his genius hint at a formal, if not fully articulated, method of trial and error and recorded solutions. From these civilizations, we inherit not only knowledge, but also the idea that knowledge should be preserved in writing and transmitted across generations. This was a monumental shift from the purely oral traditions of the past. Written records allowed for cumulative progress. Someone could build upon the successes and failures of predecessors without having to start from scratch. Over centuries, a critical mass of specialized knowledge about math, astronomy, medicine, and construction developed in these civilizations, ensuring that certain discoveries would not be lost to time. An anecdote from this era, though apocryphal, captures the spirit of early inquiry. A Babylonian scribe, while charting the planet Venus, notices that its appearance in the morning sky recurs after a certain interval. Intrigued, he rechecks older records and cross-references them. He realizes that the planet's cycle has a predictable pattern. This triggers a hypothesis that the heavens might follow consistent laws, an astonishing leap in an age when gods were seen as controlling cosmic events on a whim. Whether or not the story is literally true, it underscores the crucial shift towards seeing nature as something that could be studied systematically. By the time we approach the decline of Mesopotamian kingdoms and the waning of ancient Egyptian dynasties, a robust foundation of knowledge had been laid. Mathematics, astronomy, engineering, and medicine were all more advanced than what might be expected from purely primitive societies. This knowledge was often guarded by priestly castes or royal scribes, meaning it wasn't universally disseminated. Yet the seeds were planted. The next major evolutionary leap in scientific thought would come from the Greeks, who would take these building blocks, reflect upon them, and begin to formalize a systematic method of inquiry, one that valued reason, debate, and logical proof. Thus, the first civilizations provided the architecture upon which science would later stand. They domesticated nature to a remarkable extent, and in doing so, recognized that certain patterns governed the flow of rivers, the arc of the stars, and the structure of living bodies. They might not have called it science in our modern sense, but their legacy endures. Stone by stone, papyrus by papyrus, they erected the scaffolding for what we now call the scientific tradition. Chapter 3. The Greeks. The systematic pursuit of knowledge. When people speak of the origins of Western science, they often point to ancient Greece. This is because the Greeks, beginning around the 6th century BCE, inaugurated a method of inquiry that sought rational explanations for natural phenomena, minimizing supernatural or mythic interpretations. While they certainly inherited ideas from Egypt and Mesopotamia, the Greeks added a critical, analytical edge that would resonate through centuries. Greek science was born on the coasts of Ionia, where merchants and travelers brought stories and data from foreign lands. Philosophers like Thales of Miletus wondered if there was a single underlying substance to the cosmos. Rejecting the notion that gods or spirits controlled every natural occurrence, he posited that water might be the first principle of all things. Although oversimplified by modern standards, Thales's approach was revolutionary. He proposed a natural cause for the world's origin, subject to reason and observation. Soon, a wave of thinkers emerged: Anaximander, Anaximenes, Pythagoras, and Heraclitus, each contributing distinct views on the nature of reality. They asked questions that resonate with us even now. What is the universe made of? Why do the planets move as they do? How can we quantify the relationships between shapes and numbers? Pythagoras in particular left a lasting legacy, championing the idea that numbers and ratios underpin the fabric of reality. His famous theorem about right-angled triangles is only one example of his group's broader fascination with mathematics. The city of Athens, after its golden age under Pericles, became a hub for philosophical schools. Socrates, though less concerned with natural science, introduced a method of question and answer, dialectic, that emphasized reasoned argument. His disciple, Plato, built upon the Socratic tradition, but also wove in metaphysical concepts. Plato's realm of forms suggested that the world we see is but a shadow of a higher, unchanging reality. This philosophical view influenced how many Greek thinkers approached science. They looked for perfect, ideal principles underlying the messy chaos of everyday experience. But it was Plato's student, Aristotle, who left the deepest imprint on science for the next 2 millennia. Aristotle believed in the systematic observation of nature, classifying plants and animals, studying politics and ethics, and theorizing about physics and cosmology. Although some of his conclusions, like a geocentric universe with planets embedded in crystalline spheres, would later be revised, his methodology was groundbreaking. He insisted, that knowledge arose from empirical observation combined with logical deduction, thus setting a template for future scientific method. Greek astronomers made important strides as well. Eudoxus of Cnidus tried to model planetary motions with nested spheres. Callippus refined these models further. Then came Aristarchus of Samos, who boldly proposed a heliocentric system, placing the Sun at the center, not the Earth, centuries before Copernicus would reintroduce the idea. Although Aristarchus's view did not gain widespread acceptance then, it showcased the Greeks' willingness to challenge established assumptions. A particularly illuminating anecdote comes from Eratosthenes, the head of the Library of Alexandria, around 240 BCE. By measuring the shadows cast at noon in two different locations, Syene, modern-day Aswan, and Alexandria, he deduced that the Earth was a sphere and even calculated its circumference with remarkable accuracy. He was off by only a few percent. Eratosthenes' experiment exemplifies the Greek spirit of applying geometry and observation to solve big questions about the natural world. The Greeks also excelled in engineering and technology. Archimedes of Syracuse developed fundamental principles of hydrostatics and levers, famously crying "Eureka" upon realizing that the displacement of water in a bath could measure the purity of a gold crown. He designed war machines, pulleys, and even conceptualized infinite series. Hero of Alexandria would later invent steam-powered devices. Though relegated to entertainments and not harnessed for industrial use, they hint at how close the ancients came to proto-industrial technology. Despite these achievements, Greek science was not without limitations. Many theories were speculative, and the emphasis on geometry sometimes overshadowed experimentation. Moreover, Greek society was stratified. The practice of manual labor was relegated to slaves, and this cultural barrier may have hindered the union of theoretical speculation with practical experimentation. Yet their philosophical dedication to rational inquiry would remain a guiding light for centuries to come. The Hellenistic period, following Alexander the Great's conquests, spread Greek culture as far as India. Centers of learning like the Library of Alexandria became repositories of scrolls containing knowledge from Egypt, Babylonia, and beyond. Scholars from various backgrounds exchanged ideas and refined theories. This cross-pollination of thought was crucial. It allowed Greek methods of rational inquiry to mingle with older traditions of observation and record-keeping. By the time the Roman Empire absorbed Greece, the foundations of Western science were largely in place. The Romans, more pragmatic than speculative, would focus on large-scale engineering, roads, aqueducts, and monumental architecture, while passing along and preserving much of Greek scientific thought. Within a few centuries, these ideas would find new guardians in the Islamic Golden Age, ensuring that Greek insights were never fully lost, even as the Roman world began to crumble. Chapter 4. The Great Interregnum. Transmission of Greek knowledge through Islamic scholars. After the decline of the Western Roman Empire in the 5th century CE, Europe entered what some historians call the early Middle Ages, often caricatured as the Dark Ages. While that label is overly simplistic, local pockets of learning and monastic scholarship did persist. There was indeed a relative stagnation of scientific progress in much of Christian Europe. However, far from being globally dark, this era saw a brilliant intellectual flowering in the Islamic world, spanning from Persia to Spain. Early Islamic civilization, flourishing from the 8th to the 13th century, made the transmission and expansion of Greek knowledge a central cultural endeavor. Baghdad's House of Wisdom, Bait al-Hikmah, became a renowned center where scholars translated Greek texts into Arabic. Works by Aristotle, Ptolemy, Archimedes, and Galen were painstakingly preserved, studied, and commented upon. However, these translators and scholars did more than just copy texts. They critiqued, refined, and innovated. An emblematic figure was al-Khwarizmi, whose treatise on algebra laid the foundations for the field. His name gave rise to the word algorithm, a testament to the enduring influence of his mathematical works. Another luminary was al-Razi, a Persian physician who wrote extensively about medicine, including the differentiation of smallpox and measles. Equally famous was Ibn Sina Avicenna, whose Canon of Medicine would remain an authoritative text in both the Islamic world and medieval Europe for centuries. Astronomy also advanced dramatically. Inspired by Ptolemy's Almagest, Islamic astronomers built observatories, like the famous one at Maraga, and composed star catalogues that surpassed Greek records. They identified new stars, refined planetary models, and experimented with advanced spherical geometry. Al-Hazan ibn al-Haytham made groundbreaking contributions in optics, explaining vision as a process of light entering the eye rather than rays emanating from it. He also championed an experimental method that can be seen as a precursor to modern scientific inquiry. And yet, such accomplishments were not confined to the Middle East. In Islamic Spain, Al-Andalus, centers of learning like Córdoba thrived. Innovations in medicine, mathematics, and agriculture transformed the region into a cultural beacon. Jewish scholars such as Maimonides, writing in Arabic, wove Jewish theological thought with Aristotelian philosophy, further demonstrating the cosmopolitan interplay of ideas. Why this sudden surge of scientific activity in the Islamic world? Several factors converged. The Islamic Empire at its height spanned diverse lands, from the Indus to the Iberian Peninsula, unifying a vast trade network. This facilitated the exchange of texts and ideas. Additionally, the Quranic emphasis on knowledge, ilm, as a virtue encouraged scholarly pursuits. Wealthy patrons, including caliphs, funded these endeavors, attracted by the practical benefits of improved navigation, medicine, and agriculture. An engaging anecdote from this period involves the Abbasid Caliph al-Mansur, who reportedly summoned Indian astronomers to Baghdad to translate the astronomical treatise Siddhanta. This cross-cultural collaboration led to new star tables and advanced computations, exemplifying how the Islamic world synthesized knowledge from Greece, Persia, India, and beyond. Of course, Greek knowledge wasn't taken wholesale, it was examined critically. Thinkers like Averroes ibn Rushd in Al-Andalus wrote extensive commentaries on Aristotle, questioning and at times challenging the Greek master's conclusions. This spirit of inquiry, coupled with rigorous scholarship, bridged the gap between ancient science and the European Renaissance. By the 12th century, a cultural translation movement began to bring Arabic texts, and the Greek originals preserved within them, into Latin for Christian Europe. Scholars like Gerard of Cremona traveled to Toledo, translating works on astronomy, medicine, and mathematics. Slowly, the embers of Greek science were rekindled in European universities that were just beginning to form in cities such as Bologna, Paris, and Oxford. The stage was now set for the next epoch, a re-encounter with classical learning that would eventually blossom into the Renaissance and the scientific revolution. Thus, the so-called Great Interregnum in Europe was anything but an interregnum globally. The Middle East was teeming with intellectual vigor, forging new paths in math, medicine, and astronomy. It was through these Islamic scholars that the legacy of the ancient world was not only preserved, but enriched and returned, like a well-tended torch, to rekindle the scientific spirit in the West. Chapter 5. The Renaissance. A new dawn of discovery. By the 14th and 15th centuries, Europe began to awaken from feudal isolation. The Renaissance, literally rebirth, took root in Italian city-states like Florence, Venice, and Milan, spreading northward over the next 2 centuries. This cultural flourishing wasn't limited to art and literature, it also reignited a passion for the natural world and for the ancient texts that described it. The invention of the printing press by Johannes Gutenberg around 1440 was a game-changer. Books, once laboriously copied by hand and too expensive for most, suddenly became more widely available. Greek and Arabic works of science, newly translated into Latin, circulated among scholars who were rediscovering classical thought. This democratization of knowledge broke the monopoly held by ecclesiastical and monastic institutions. Universities opened across Europe, and a reading public with some disposable income emerged, a fertile ground for new ideas. One milestone was the rediscovery of works by the Greek geographer Ptolemy. His geography, reintroduced to Europe, helped navigators chart the seas, fueling the age of exploration. Sailors such as Vasco da Gama and Christopher Columbus embarked on voyages that tested scientific knowledge and garnered new data about the world. The horizon quite literally expanded, forcing scholars to reconcile new discoveries, continents, peoples, and flora with classical theories. Art, science, and engineering began to mingle in extraordinary figures like Leonardo da Vinci. Often described as a polymath, Leonardo dissected human cadavers to understand anatomy, designed flying machines inspired by birds, and studied the flow of water and the refraction of light. Though he didn't publish formal scientific treatises, his notebooks brimming with sketches and mirror-script commentaries are testaments to the Renaissance spirit, a boundless curiosity unfettered by institutional constraints. Meanwhile, Nicholas Copernicus quietly revolutionized astronomy. In his work, De Revolutionibus Orbium Coelestium, published in 1543, he proposed a heliocentric model, placing the Sun at the center of the cosmos. He cited the complexities of Ptolemaic epicycles as a motivating factor to explore a simpler arrangement. Though not immediately accepted, some vehemently opposed the idea. Copernicus's theory cracked open the door to a new understanding of celestial mechanics. Europe's intellectual atmosphere buzzed with controversy and innovation. Medical progress also leapt forward. Andreas Vesalius published De Humani Corporis Fabrica in 1543, providing detailed anatomical illustrations based on first-hand dissections, challenging centuries of blindly accepted Galenic doctrines. In the field of mathematics, Girolamo Cardano, Niccolo Tartaglia, and others laid the foundations for complex numbers and further algebraic techniques, building on the Arabic and Greek legacies. An iconic anecdote from this era involves the mathematician and astronomer Regiomontanus, Johannes Müller. A fervent believer in the power of printing, he established one of the earliest printing presses dedicated to scientific literature. Among his published works was a revised version of Ptolemy's Almagest, which would inspire younger astronomers, including Copernicus. This demonstrates how the Renaissance hinged upon a synergy of technology, printing, rediscovery of ancient texts, and the audacious questioning of old assumptions. In tandem with these academic pursuits, the Renaissance was also a time of patronage by wealthy families, such as the Medici of Florence. They financed artists, architects, and scholars, competing in a friendly rivalry to commission the greatest masterpieces. This patronage system fostered a climate of creativity where cross-disciplinary endeavors could thrive. An artist might consult astronomers to design better perspective in paintings. An engineer might partner with mathematicians to build more accurate clocks. Yet the Renaissance also sowed seeds of tension with religious authorities. The Protestant Reformation had shattered the unity of Western Christendom, leading to conflicts that sometimes overshadowed scientific questions. Still, in many courts and universities, intellectual freedom was on the rise. As the 16th century progressed, a chain reaction was set off that would lead to the full-blown scientific revolution of the 17th century. Thus, the Renaissance stands as a critical link between the medieval world, where knowledge was curated and at times stifled by ecclesiastical powers, and the modern era of open inquiry. It was a period of reawakening fueled by the printing press, the rediscovery of classical knowledge, and the swirling currents of social change. The next step would be to refine these new perspectives into a systematic approach to investigating reality, a method that would reshape humanity's relationship with the cosmos. Chapter 6: The Age of Reason. The Scientific Revolution and the Foundation of the Scientific Method. Stepping into the 17th century, Europe bristled with intellectual excitement. This era, often called the Scientific Revolution, introduced a new wave of thinkers who believed that systematic observation and mathematical reasoning could unlock nature's mysteries. The Age of Reason is not an overstatement. It was a time when people like Galileo Galilei, Francis Bacon, and René Descartes declared that human reason, empowered by careful experiment, was the path to reliable knowledge. One key figure was Francis Bacon, who championed a method of empirical inquiry he detailed in works like Novum Organum, 1620. Rejecting medieval scholasticism, Bacon argued that science should progress from specific observations to general axioms, an inductive method. He famously warned against idols or systematic errors of thought, which he categorized as idols of the tribe, human nature, the cave, individual biases, the marketplace, confusions of language, and the theatre, philosophical dogmas. This call to purge biases and rely on direct experimentation would heavily influence the ethos of modern science. Galileo Galilei took up the mantle of experimentation with fervor. Often called the father of modern science, Galileo used telescopes to study the heavens, discovering moons around Jupiter, mountains on the moon, and phases of Venus, evidence supporting Copernicus's heliocentric theory. In mechanics, he famously studied falling bodies, measuring how objects accelerate uniformly regardless of weight, neglecting air resistance. Through a blend of experiment and mathematical description, Galileo defied Aristotelian physics and faced scrutiny from the Church for his astronomical views. Meanwhile, René Descartes proposed a rationalist philosophy. In his Discourse on Method, 1637, he asserted cogito ergo sum, I think therefore I am, as a first principle. For him, knowledge could be built on indubitable truths identified through reason alone. While Bacon emphasized inductive reasoning from observations, Descartes championed deductive reasoning from self-evident principles. Despite their differences, both philosophers valued systematic rigor, marking a new standard for scientific inquiry. This era also saw a growth in scientific societies, most notably the Royal Society of London, founded in 1660, and the Académie des Sciences in Paris, 1666. These institutions provided platforms for scientists to discuss findings, critique each other's experiments, and publish results. Journals such as Philosophical Transactions shared breakthroughs with an increasingly literate European public. The concept of peer review, though rudimentary at first, began to take shape, ensuring that claims were scrutinized before acceptance. An illustrative anecdote from the Royal Society's early days involves Robert Boyle, who carefully documented his air pump experiments. He showed that sound required a medium and that a candle flame extinguished in a vacuum. These experiments, often open to public demonstration, helped usher in a culture of replicable science, where public witnessing of experiments was part of the validation process. Isaac Newton would soon become the exemplar of this period's triumphs. In 1687, he published the Philosophiae Naturalis Principia Mathematica, laying out the laws of motion and universal gravitation. His work synthesized the insights of Galileo and Kepler into a coherent framework describing celestial and terrestrial mechanics. Remarkably, Newton used mathematics, specifically calculus, which he co-developed, to show that the force keeping planets in orbit around the Sun is the same force causing objects to fall on Earth: gravity. This unification of heaven and earth under one set of laws was a crowning achievement of the scientific revolution. Yet science was not a purely European affair. Correspondences with Jesuit missionaries in China, as well as with merchants and explorers in the New World, brought new data on geography, botany, and zoology. This growing body of knowledge pushed Europeans to refine classification systems. The intellectual developments of the 17th century thus rested on a global foundation, albeit one often marked by colonial exploitation and uneven power dynamics. By the dawn of the 18th century, the stage was set for science to become a primary driver of societal and technological change. The scientific revolution had formalized the notion that experiments, mathematics, and reason were the pillars of reliable knowledge. Although theological and philosophical disputes persisted, the basic framework of the scientific method, observation, hypothesis, experiment, and conclusion, was firmly established. The next phase, the Enlightenment, would see these principles applied to broader questions of society, economics, and governance. Thus, the Age of Reason stands as a watershed in human intellectual history. The seeds planted by Bacon, Descartes, Galileo, and Newton would grow into the robust institutions and practices we associate with modern science. The idea that the universe follows consistent, discoverable laws became taken for granted in many circles, paving the way for the next leaps in understanding. Chapter 7: Galileo, Newton, and the Laws of Nature. While Galileo and Newton often appear as towering solitary geniuses in popular accounts, their achievements were interwoven with the broader tapestry of 17th century science. Nonetheless, these two figures exemplify the shift from a medieval worldview, where knowledge was primarily deduced from ancient authorities, to a modern one grounded in systematic observation and mathematical description. Galileo's run-in with the Roman Catholic Church is perhaps the most famous anecdote from this era. In 1610 he published Sidereus Nuncius, announcing his telescopic discoveries, lunar mountains, a multitude of stars invisible to the naked eye, and the 4 largest moons of Jupiter. His observations contradicted the Aristotelian Ptolemaic cosmos, which held that all heavenly bodies revolved around the Earth and that celestial spheres were unblemished. Even more shocking was his observation of Venus's phases, which strongly suggested that the planet orbited the Sun. Galileo's championing of the Copernican system placed him in conflict with church authorities. Tried by the Inquisition in 1633, he was forced to recant his heliocentric views publicly and spent the remainder of his life under house arrest. Yet his dialogue concerning the 2 chief world systems had already been widely read, seeding scientific circles with the notion that the Earth moved around the Sun. Despite condemnation, Galileo's work remained influential, testifying to the unstoppable momentum of empirical science. Meanwhile, Isaac Newton was born in the year Galileo died, 1642, a symbolic passing of the torch between generations of scientific giants. Newton's early years were marked by a mixture of brilliance and isolation. At Cambridge, he immersed himself in mathematical and physical investigations, laying the groundwork for calculus, though the credit for its invention would be disputed with Gottfried Wilhelm Leibniz. Newton explored optics, revealing that white light is composed of the full spectrum of colors, a discovery he demonstrated using prisms in his darkened chamber at Trinity College. His magnum opus, the Principia, published with the encouragement and partial financing of Edmund Halley, delineated the 3 laws of motion and the law of universal gravitation. This was more than a breakthrough in physics. It was a grand unification of terrestrial and celestial phenomena. The orbits of planets, the trajectory of comets, and the fall of apples from trees all obeyed the same fundamental laws. Newton's mathematical framework provided predictive power, enabling astronomers to chart celestial motions with astonishing accuracy. An often recounted anecdote, though likely embellished, claims that Newton was inspired to think about gravity after seeing an apple fall from a tree. Whether or not that exact scene occurred, there is a grain of truth. Newton did reflect on everyday experiences, linking them to cosmic principles. The brilliance was in seeing that the same force acting on a falling apple extends, by inverse square relationship, throughout the cosmos. Galileo and Newton also advanced the notion that mathematics was the language of nature. Galileo famously wrote, "Philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze. But it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics." This viewpoint, that the laws of nature are fundamentally mathematical, would profoundly shape the trajectory of modern science. Both men encountered controversies and rivalries. Galileo clashed with church authorities, as well as with Aristotelian philosophers. Newton had acrimonious disputes with Leibniz over calculus, and with Robert Hooke over the nature of light and gravity. These disputes reveal that scientific progress has never been a purely harmonious enterprise. It is often driven by intense competition and debate, which can spark new ideas or entrench old biases. By the time Newton died in 1727, the world had changed. Astronomy had moved from geocentrism to heliocentrism. The laws governing motion had been expressed in elegant mathematical form. A mechanistic worldview was ascendant, envisioning the universe as a grand clockwork set in motion by precise laws. Science was no longer a sideline curiosity for monks or curious aristocrats. It was a growing enterprise, shaping how people thought about everything from navigation to theology. Thus, Galileo and Newton symbolized the moment when the intellectual scaffolding for modern science was firmly put in place. Their willingness to experiment, challenge authority, and describe nature mathematically inspired future generations. Whether through conflict or discovery, their legacy established the bedrock for the Enlightenment and beyond, setting the stage for the ever-expanding domain of physics, astronomy, and the sciences as a whole. Chapter 8: Enlightenment Thinkers and the expanding realms of science. The 18th century is often called the Enlightenment, an era where reason and empiricism were celebrated as the keys to understanding not just nature, but also society, politics, and human behavior. Thinkers like Voltaire, Montesquieu, and Jean-Jacques Rousseau applied rational critique to government and social structures, while scientists continued the legacy of Galileo and Newton, pushing the boundaries of knowledge further. Across Europe, salons hosted by wealthy patrons, often women, served as informal intellectual gatherings where ideas from science, philosophy, and literature intermingled. Encyclopedists such as Denis Diderot and Jean-Laurent d'Alembert compiled vast works summarizing human knowledge, reflecting a new confidence in the rational organization of learning. The Enlightenment was also a time when scientific societies and academies proliferated, institutionalizing research and providing stable platforms for publishing scientific findings. In Britain, the Royal Society flourished, boasting members like Edmund Halley, who predicted the return of the comet that now bears his name, and Joseph Banks, who travelled with Captain James Cook to the South Pacific, cataloguing an astonishing array of flora and fauna. Such expeditions expanded the realm of biology and geology, exposing Europeans to new species and geological formations, prompting questions about the age of the Earth and the diversity of life. A major development in this period was the rise of chemistry as a rigorous science. Robert Boyle had laid its philosophical groundwork in the 17th century, but it was Antoine Lavoisier who revolutionized it. Often called the father of modern chemistry, Lavoisier identified and named oxygen and hydrogen, understood the role of oxygen in combustion, and helped formulate the law of conservation of mass. His systematic experiments and precise measurements replaced the mystical alchemy tradition with a quantitative discipline. Alongside Lavoisier, other luminaries like Joseph Priestley and Henry Cavendish contributed to understanding gases and elements. Meanwhile, in the 18th century, Linnaeus in Sweden pioneered the taxonomic classification of living organisms, introducing the binomial nomenclature, genus and species, still in use today. By providing a systematic way to categorize plants and animals, Linnaeus's work spurred further study of biodiversity, shaping the future of biology and ecology. One enlightening anecdote involves the English physician Edward Jenner, who in 1796 performed an experiment on an 8-year-old boy to test the protective effect of cowpox against smallpox. This marked the inception of vaccination, a practice that would eventually save countless lives worldwide. Jenner's method combined observation, milkmaids who contracted cowpox didn't get smallpox, with empirical testing, a hallmark of Enlightenment science's focus on real-world applications. Enlightenment scientists also delved deeper into physics. The Bernoulli family in Switzerland made strides in fluid dynamics, culminating in Daniel Bernoulli's Hydrodynamica. Leonhard Euler, one of the most prolific mathematicians of all time, tackled problems from celestial mechanics to number theory. His works, along with those of the French mathematician Joseph-Louis Lagrange, extended Newtonian mechanics and laid the groundwork for much of modern mathematical physics. However, the Enlightenment also had its dark edges. The era's confidence in reason led some philosophers and scientists to justify colonial exploitation or to uphold racial hierarchies under the guise of scientific racism. Phrenology and physiognomy, pseudo-scientific attempts to link cranial shape or facial features with intelligence and character, gained popularity in some circles. These misapplications highlight how science, while enlightening in many ways, can be twisted to serve unjust agendas. Nevertheless, by the close of the 18th century, science had expanded dramatically. The mechanical worldview inherited from Newton was enriched by discoveries in chemistry, biology, and geology. The Enlightenment's faith in progress through knowledge set the stage for the Industrial Revolution, where technological innovations would transform societies at an accelerating pace. As the 19th century dawned, the fervor for classification and discovery intensified, eventually bringing forth dramatic theories on the origins of life and the workings of the earth. Thus, the Enlightenment not only carried forward the scientific tradition, but broadened its scope to encompass all facets of human life. Reason, systematic experimentation, and empirical data became ideals, even if reality often fell short. In the century that followed, these ideals would be tested and expanded upon, culminating in profound paradigm shifts and the birth of modern disciplines. Chapter 9. The 19th Century. Industrial Revolution, Darwin, and the Explosion of Knowledge. The 19th century witnessed an unprecedented convergence of scientific breakthroughs and technological progress, fueled by the Industrial Revolution. Steam engines, mechanized textiles, railways, and urbanization reshaped societies. Meanwhile, scientific institutions grew in number and prestige, fostering discoveries in everything from electromagnetism to biology. One of the century's defining characteristics was the interplay between theoretical discoveries and practical applications. Michael Faraday's experiments with electricity and magnetism, for instance, laid the groundwork for electric motors and generators. Using rotating coils in magnetic fields, Faraday demonstrated the principle of electromagnetic induction in 1831, an insight that underpins modern power generation. Faraday's humility, he was born into a poor family, and relentless curiosity exemplify the possibility of upward mobility through scientific endeavor in an era otherwise marked by social stratification. James Clerk Maxwell, building on Faraday's insights, formulated the classical theory of electromagnetism in the 1860s. His set of equations unified electricity, magnetism, and light, showing that light itself is an electromagnetic wave. Maxwell's equations would eventually pave the way for radio communication, radar, and an understanding of the electromagnetic spectrum that extends from X-rays to gamma rays. In parallel, chemistry made huge strides. Dmitry Mendeleev, a Russian chemist, published his periodic table in 1869, ordering elements by atomic weight and revealing patterns in their chemical behavior. Remarkably, he predicted the existence and properties of then unknown elements like gallium and germanium, which were later discovered, confirming the power of the periodic law. This new systematic understanding of matter had profound implications for industry, medicine, and our overall grasp of the natural world. Biology, too, underwent a transformation. Charles Darwin's On the Origin of Species, in 1859, introduced the theory of evolution by natural selection, revolutionizing our understanding of life's diversity. Darwin's meticulous observations from his voyage on HMS Beagle, 1831-1836, combined with years of painstaking study of barnacles, pigeons, and earthworms, culminated in a theory that proposed a common descent for all species and a mechanism, natural selection, for how adaptations arise. Though greeted with controversy, Darwin's theory rapidly gained acceptance among scientists, sparking debates that continue to this day. An anecdote often told about Darwin is his anxiousness to publish. Alfred Russel Wallace, working independently in Southeast Asia, sent Darwin an essay outlining an almost identical theory of evolution by natural selection. This spurred Darwin to publish his own findings earlier than intended. The two men shared credit initially, with Darwin's seminal book solidifying his legacy. It underscores the idea that major discoveries often arise in multiple minds simultaneously as the cultural and scientific milieu reaches a tipping point. Geology, meanwhile, challenged biblical chronologies. Charles Lyell's Principles of Geology, 1830-1833, argued that the Earth was shaped by slow, gradual processes, uniformitarianism, not just catastrophic events like floods or divine interventions. His estimates for Earth's age vastly exceeded previous calculations, aligning better with Darwin's timescales for evolutionary change. Natural theology and literal interpretations of Scripture were increasingly scrutinized in light of these new scientific narratives. Advances in medicine also soared, improving public health and life expectancy in many places. Louis Pasteur's germ theory of disease refuted the notion of spontaneous generation and led to pasteurization, vaccines, and antiseptic techniques. Joseph Lister applied carbolic acid to surgical instruments and wounds, drastically reducing infection rates. Another milestone was the isolation and understanding of anesthesia, making surgeries far less traumatic. Yet the 19th century was also a time of profound social upheaval. Imperial powers used new technologies, steamships, railroads, and improved firearms to conquer territories. Scientific racism found footing, with some seeking to justify colonialism through distorted interpretations of Darwinian theory. Nonetheless, the same science that enabled conquest also fueled humanitarian causes, the fight against diseases like cholera and eventually the early calls for conservation. By 1900, the velocity of progress seemed unstoppable. The seeds of modern physics were sown as scientists scrutinized the behavior of light and atoms, hinting at quantum phenomena. The industrial boom, fueled by coal and steam, had both raised living standards and polluted the skies of major cities. The promise of technology to solve human problems was at an all-time high, setting the stage for the 20th century's even more dramatic transformations. Thus, the 19th century saw science fully entwined with society, driving monumental changes in culture, industry, and worldview. The boundaries of knowledge expanded at a dizzying pace, forging the modern world and sowing the seeds for the revolutions to come in the atomic and digital ages. Chapter 10. The 20th Century. Relativity, quantum physics, and the atomic age. As the 20th century dawned, many scientists believed physics was largely complete, that only a few details needed tidying up. This complacency was shattered by two revolutionary theories, relativity and quantum mechanics. Albert Einstein's Annus Mirabilis papers of 1905 introduced the special theory of relativity, the concept of mass-energy equivalence, E equals sign mc2, and explained the photoelectric effect in quantum terms. Within a decade, he extended his ideas into general relativity, 1915, offering a new conception of gravity as curvature of space-time. Einstein's theories had staggering implications. Not only did they reframe our understanding of space and time, but they also predicted phenomena like gravitational lensing and frame dragging, effects confirmed decades later. Meanwhile, Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed the framework of quantum mechanics. Their equations showed that at atomic and subatomic scales, particles behave in probabilistic ways, challenging classical determinism. Heisenberg's uncertainty principle stated that one cannot simultaneously know a particle's position and momentum with absolute precision, undermining the mechanistic predictability of Newtonian physics. These radical changes did not come easily. The famous Solvay conferences brought together luminaries who debated the nature of reality itself. Einstein quipped, "God does not play dice," to express his discomfort with quantum indeterminacy, while Bohr countered that the universe might be inherently probabilistic. The debates were spirited, but quantum theory proved indispensable for explaining atomic spectra, chemical bonds, and eventually transistors and lasers. Another momentous development was the rise of nuclear physics. Ernest Rutherford discovered the atomic nucleus in 1911 and later performed experiments revealing the proton. James Chadwick discovered the neutron in 1932, completing the basic picture of atomic structure. These discoveries led to nuclear fission research, culminating in the Manhattan Project during World War II. The result, atomic bombs dropped on Hiroshima and Nagasaki in 1945, ushering in the atomic age. An anecdote from the Manhattan Project underscores the moral quandaries entwined with scientific progress. Physicist J. Robert Oppenheimer, upon witnessing the first successful nuclear test in 1945, recalled words from the Hindu scripture Bhagavad Gita, "Now I am become death, the destroyer of worlds." This chilling reflection highlights the dual nature of scientific discovery. The same knowledge that enlightens can be weaponized with devastating consequences. Yet the 20th century also saw science harnessed for more hopeful goals. Antibiotics like penicillin, discovered by Alexander Fleming in 1928, saved countless lives by combating bacterial infections. Vaccines proliferated, drastically reducing diseases such as polio and smallpox. Space exploration took flight. Sputnik, 1957, Yuri Gagarin's orbit, 1961, and Apollo 11's moon landing, 1969, demonstrated humanity's reach beyond our planet. In biology, The discovery of the structure of DNA by James Watson and Francis Crick, with key contributions from Rosalind Franklin and Maurice Wilkins, in 1953, revolutionized our understanding of heredity. The double helix model showed how genetic information is stored and replicated, heralding the era of molecular biology and biotechnology. By the late 20th century, the Human Genome Project was underway, mapping the entire human genetic code. Computer science, too, emerged as a dominant field. Alan Turing's theoretical work on computation laid the groundwork for digital computers. By mid-century, machines like the ENIAC and later personal computers in the 1970s and 1980s transformed how data was processed, eventually leading to the Internet, perhaps one of the most transformative technologies in human history. In this whirlwind of breakthroughs, the scientific method remained the guiding principle, hypotheses tested by experiment, peer review, and reproducibility. However, big science also emerged, where massive collaborations and government-funded projects, like CERN for particle physics or NASA for space exploration, became the norm. The scale and complexity of research grew dramatically, sometimes distancing the solitary genius model of the past. By 2000, the frontiers of science were pushing into cosmology, dark matter and dark energy, quantum computing, genetic engineering, and climate science. The 20th century left a complex legacy, dazzling achievements that expanded human potential, alongside deep ethical dilemmas about nuclear weapons, environmental impact, and the commodification of knowledge. The scientific method, refined and tested over centuries, continued to be our best tool for illuminating reality, even when the answers raised more questions than ever. Chapter 11. The Modern Era. The Information Age, Big Science, and Future Horizons. At the dawn of the 21st century, humanity stands on the shoulders of millennia of inquiry. The scientific method, formalized in the Renaissance and polished through the scientific revolution and Enlightenment, remains our primary way of understanding the universe. Yet the scale, speed, and interconnectedness of modern science would be unrecognizable to past ages. The information age, ignited by advances in computing, has revolutionized how scientists work. High-speed internet, massive data storage, and cloud computing enable global collaborations and unprecedented data analysis. Astronomers use arrayed telescopes to gather terabytes of data each night, while particle physicists at the Large Hadron Collider sift through petabytes of collision events, searching for evidence of new particles. Machine learning algorithms help interpret complex datasets in fields as diverse as genomics, climate modeling, and social science. The discovery of the Higgs boson in 2012 stands as a testament to big science. Thousands of scientists from over 100 countries collaborated on experiments at CERN. Their success confirmed a half-century-old theoretical prediction in the Standard Model of particle physics, reinforcing the power of collective effort. Similarly, gravitational waves, predicted by Einstein a century earlier, were first directly detected in 2015 by the LIGO-Virgo collaboration, another example of large-scale, multinational cooperation pushing the boundaries of human knowledge. Biology and medicine have undergone similarly transformative shifts. Gene editing techniques like CRISPR-Cas9 promise to reshape fields from agriculture to human gene therapy. Synthetic biology aims to design organisms with novel functions, triggering debates about ethics, biosafety, and bioterrorism. Meanwhile, the global COVID-19 pandemic, starting in 2019-2020, showcased both the capabilities and limitations of modern science. Vaccines were developed at record speed, but misinformation and political strife hampered unified responses. Space exploration also continues to expand. Private companies like SpaceX and Blue Origin are vying with national agencies like NASA, ESA, and CNSA to lower the cost of orbital launches and target deeper ventures into space. Rovers on Mars, probes around Jupiter and Saturn, and telescopes like the James Webb Space Telescope promise new insights into planetary science, exobiology, and cosmology. The question of whether life exists elsewhere remains as tantalizing as ever, spurring missions to Mars, Europa, and beyond. Yet our era faces formidable challenges. Climate change threatens ecosystems and human societies, microplastics pollute oceans, and the loss of biodiversity accelerates. Science has illuminated these problems, but solutions require political will, global cooperation, and a shift in economic paradigms. As in past eras, the relationship between science and society remains intertwined with ethical, social, and geopolitical concerns. Looking to the future, quantum computing could revolutionize data processing, artificial intelligence could transform labor markets, and new materials might lead to breakthroughs in energy storage. The accelerating pace of discovery raises hopes for eradicating diseases and colonizing other planets, yet also fears of looming crises, from cybersecurity to global pandemics. How we wield scientific knowledge will determine whether we steer toward utopia or catastrophe. In sum, the story of science is one of relentless curiosity, of humans striving to understand the cosmos and their place within it. From prehistoric tally marks to quantum supercomputers, we have repeatedly questioned the known and ventured into the unknown. The scientific method, with its cycles of hypothesis, experiment, observation, and revision, remains our best compass in an ever more complex world. Epilogue. Though we have reached the present day, the history of science is ongoing, its next chapter unwritten. New theories will overturn old assumptions, fresh perspectives will emerge from unanticipated corners. In the vast tapestry of the universe, each scientific discovery is but a single thread, weaving together to form an ever-shifting picture. As we continue this grand enterprise, this pageant of trial and insight, let us remember the wonder that animated our earliest ancestors, who looked at the sky and asked, "Why?" It is that same wonder, guided now by rigorous method and global collaboration, that lights our path forward into the boundless possibilities of tomorrow.